is about to dig up the facts about the elements known as the other metals.
First, we'll discover the fundamental features of this useful group of elements in exploring other metals.
Then we'll see how the most abundant metal on Earth brings electrical power to our homes, schools, and offices in aluminum, providing power.
Next, we'll examine how one of the properties of the metal tin may have played a role in the demise of France's Grand Army. In tin, Napoleon's nemesis.
Then we'll see how lead-lined aqueducts may have slowly poisoned the people of the Roman Empire in Lead, Rome's poisoned plumbing.
And finally, we'll take a look at how aluminum, other elements, and emerging technologies are transforming transportation in Future of the Car.
Elements that bring us power and take it away. Coming up next. As you watch the first half of this program, keep these questions in mind.
What properties do the other metals share?
Why did the Romans use lead in their plumbing?
The group of elements known as the other metals contains some of the most widely used elements in modern society. If you've ever drunk from a can of soda or wrapped leftovers in metal foil, chances are you've just used one of the other metals.
What do you know about the other metals?
Aluminum is another metal. It's used in aluminum foil. It's an insulator because it keeps food insulated, either hot or cold.
Tin is used for canned goods because it's easy, it doesn't break easily, and it can keep whatever it holds, it keeps from damaging.
Tin is a very cheap metal, so a lot of companies use it for like sodas or anything to contain liquids.
Lead used to be in pencils, but now there's graphite because lead was found to be poisonous.
Sometimes they put aluminum siding on a house because it's a good insulator.
The other metals are the metallic elements located between the transition metals and the metalloids on the periodic table. Compared with the transition metals, the other metals are generally softer, have lower boiling and melting points, and are more electropositive. Aluminum is a silver-white metal that makes up 8% of the Earth's crust. Although it is the most abundant metal on the planet, it is never found in its pure form. Instead, it must be separated from other minerals by a complicated electrolysis process. Aluminum is used in millions of products across the globe, and it is the most commercially important of the other metals. It is the main metal in electrical transmission wires. Gallium is a blue-gray metal that is used to produce semiconductors, transistors, quartz thermometers, and low-melting alloys. A compound of the element gallium arsenide can produce laser light directly from electricity. Indium goes into solar and photo cells, transistors, mirrors, nuclear power regulators, and as a coating for high-speed bearings. Tin is a silver-white metal that can be found in nature in its metallic state. Tin has good resistance to corrosion. Tin plating, placing a thin layer of protective tin coating over other metals, is the primary use of the element today. Tin becomes brittle at very low temperatures, and some believe that this property may have contributed to Napoleon's defeat during the freezing Russian winter. Thallium is a poisonous soft silver-grain metal that has no uses in its pure form because it readily combines with oxygen and water vapor to form a black powdery substance. Thallium compounds are used to create low-melting glass and alloys and to make infrared radiation detectors. Lead is a soft, silver-blue, corrosion-resistant metal that darkens rapidly when exposed to air. Today, lead is used in many products, including storage batteries, solder, metal alloys, and radiation shielding. Lead has been known since ancient times. The Romans used lead to line their aqueducts and make water pipes. But prolonged exposure to this element can be deadly, which may have contributed to the fall of Rome's great empire. Bismuth is a white brittle metal with a slight pink tint. It resists becoming magnetized more than any other metal. It also is the least heat-conducting metal after mercury. Bismuth is used to manufacture metal alloys, acrylic fibers, plastics, electrical fuses, and automatic fire sprinkler systems. All other metals are opaque metallic elements that have relatively high densities. These elements are generally ductile and bendable, like the transition metals, and they also exhibit some very different properties. Compared to the transition metals, the other metals are generally softer and have lower boiling and melting points. Their atoms are more electropositive, meaning that they lose valence electrons more easily than the transition metals. These differences can be explained by taking a closer look at where the other metals reside on the periodic table. On the periodic table, the elements are listed in order of their atomic number. The atomic number represents the number of protons in an element's nucleus. In its normal or ground state, this nucleus is also surrounded by an equal number of electrons. And as the atomic number increases, generally so does the size and mass of the atoms. As you read the periodic table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. For example, there are 4 electron shells in an atom of gallium, so it lies in period 4. Meanwhile, an atom of thallium in period 6 has 6 electron shells. As you read across the table from left to right, the vertical lines of elements are called groups. Elements in one group have the same number of electrons in their outermost electron shells. These are called valence electrons, and they dictate how elements interact. Did you know? Sometimes the other metals are called the poor metals. They get this name because they are very soft and weak and have lower melting points than most metals, but they are not poor in usefulness. Many of the other metals, especially aluminum, lead, and tin, have hundreds of uses in modern society.
The modern world relies on electricity and the aluminum electrical transmission lines that bring it to our schools, homes, offices, and public spaces.
What would you do without electricity?
Well, I can do everything I normally do, except for, use my computer.
Yeah, I wouldn't be able to go online, watch TV, talk on the phone.
Open the refrigerator, use the microwave.
Heating, air conditioning.
I'd have to go to bed at 7 o'clock, couldn't listen to the Walkman or the radio.
I'm not sure exactly what I'd do for entertainment. I'd probably spend a lot more time outside.
Go outside. I love hiking anyways. And I'd probably knit because I like to knit. And I don't know, sit around the fire.
I would tone things down and try to live a more simple life and really try to become more familiar with natural things. Without electricity, the days would be shorter because I wouldn't be able to stay up late. You wouldn't be able to get up too early.
I'd probably spend my time inside reading a book, drawing, arts and crafts, things like that.
I can't think of anything else, I'm sorry.
Element number 13 on the periodic table is aluminum. The atomic symbol for aluminum is Al. Aluminum, a soft, silver-white metal, is an excellent conductor of heat and electricity. It is also non-magnetic, non-sparking, and the second most malleable metal after gold. Aluminum gets its name from the Latin word alumen, meaning alum, one of the compounds that contains the element. Aluminum is classified as an other metal and lies on the third row of the periodic table, called period 3. Each atom of aluminum consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of aluminum, the nucleus has 13 positively charged protons and 14 uncharged neutrons. Aluminum has 13 negatively charged electrons to balance its 13 protons. These electrons are found in 3 shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, neon. Neon has 10 electrons distributed among 2 electron shells. The 3 additional electrons in aluminum determine its unique chemical behavior. The first 2 are found in the sphere-shaped 3s orbital shell. The remaining electron is found in one of 3 lobe-shaped 3p orbitals. Aluminum typically reacts by transferring its 3 valence electrons to nonmetals. Pure aluminum is a relatively reactive metal, but the I-beam shown in this experiment has formed a protective transparent oxide layer on its surface because it has been exposed to air. A small piece of gallium metal, which has a very low melting point, is melted onto the I-beam using a hot air gun, and a syringe is used to scratch the aluminum through the molten gallium. Next, the syringe is used to collect a small amount of mercury. When the mercury is mixed with the gallium, the 2 metals form an amalgam, which destroys the protective oxide coating and allows the exposed aluminum to corrode. This process occurs over a few hours and is shown here in time-lapse. Because of the destructive effect mercury and gallium have on aluminum, they are banned from being transported on airplanes, which are largely made from aluminum alloys. Aluminum is the most abundant metal on the planet, but it is never found in its pure form. Once it is separated from the compounds it is found with, it can be turned into millions of useful products. Aluminum's lightness and durability make it ideal for making everything from vehicle parts to building materials to baseball bats. And since it resists rust, it is also used for making everything from soda cans to nails to the staples in tea bags. Coney Island in New York was one of the first places in the nation to receive electricity. The inventor Thomas Edison ran electrical transmission wires through the park, bringing power to his newly invented incandescent bulbs. We've come a long way since the lights were first turned on at the turn of the 20th century. Today, electrical transmission lines stretch across the country, reaching even the most remote corners. The metal copper was first used for transmission wires because it conducts electricity so well. But after World War II, copper was replaced by aluminum in high-voltage lines. Although atoms of aluminum conduct electricity only about 60% as well as those of copper, aluminum is 3 times lighter. So a pound of aluminum can actually carry twice as much electricity as a pound of copper. Today, almost all transmission lines and many transmission towers are made of aluminum, and delivering electrical power is the single largest use for the metal. These aluminum lines often carry 500,000 volts. When something goes wrong with one of these high-voltage tension lines, it's up to the linemen to make the repairs. And they usually do it without shutting down the power. A daring aerial technique is often used to repair the lines.
It's pretty dangerous, I feel, because you're mixing aviation with electricity. One, you're depending on the helicopter, everything mechanical to go right. If it goes wrong, you're going to drop out of the sky like a rock. If the lineman makes a mistake, you're going to vaporize.
These linemen and pilots are a few of the handful of people in the world qualified to make aerial repairs. But the dangerous mix of helicopters and power lines saves money and time. It takes the aerial crew only hours to make repairs that would take a conventional ground crew days.
This is the span that we want. I'm going to go ahead and come down in between the the two 500 kV lines, and we're going to find the damage location, and we'll get ready to start work.
We could actually get too close to a power line and a tree, and the electricity would arc amongst all of us, and we could actually short out the power line and destroy ourselves.
Working on these high-voltage aluminum lines is a dangerous job, one that requires special equipment, steady nerves, and years of training. And it takes brave men and women like these to make sure our homes, offices, schools, and everywhere else continue to receive the electricity they need. Did you know? Although aluminum never occurs freely in nature in the metallic form, its compounds are present in almost all rocks, vegetation, and animals. Aluminum is concentrated in the outermost 10 miles of the Earth's crust, and it is the third most abundant element after oxygen and silicon.
Despite assembling one of the greatest armies the world had ever seen, Napoleon Bonaparte was unable to take over the Russian Empire during his 1812 invasion. In a fatal failure of leadership, Napoleon allowed his army to be defeated not by enemy troops, but by the Russian winter. Do you know of any great failures of leadership?
Stalin, because he oppressed his people.
Gorbachev, because his Soviet Union didn't meet the needs or the desires of the Soviet people.
Saddam Hussein, because he was oppressive. He got involved in a lot of wars.
I would say George III, because he lost the colonies. He was too worried about himself, and he wasn't well educated, and he lost probably their most important source of revenue until the British took India.
Element number 50 on the periodic table is tin. The atomic symbol for tin is Sn. Tin is a lustrous, soft, bendable silver-white metal that is very resistant to rust. Tin's unusual atomic symbol, Sn, comes from stannum, the Latin word for tin. Tin is classified as an other metal and lies in the periodic table's 5th row, period 5. Each atom of tin consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of tin, its nucleus has 50 positively charged protons, plus 69 uncharged neutrons. Tin has 50 negatively charged electrons to balance its 50 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed among 4 orbital shells. Tin has 14 more electrons than krypton. The first 2 electrons are found in the sphere-shaped 5s orbital shell. The next 10 electrons fill 5 clover-shaped 4d orbitals. And the final 2 electrons are distributed among 3 lobe-shaped 5p orbitals. Since the electrons in the 4d orbital are at a lower energy than those in the 5s and 5p orbitals, only the 4 valence electrons in this 5th shell influence how tin interacts with other elements. Ordinary tin is a silvery white metal that is easy to work with. A thick piece of tin is shown here being flattened out in a press. When the piece of tin is bent, the metal's atoms, which form a crystalline structure, produce a crackling sound that is known as a tin cry. Since tin does not react readily with oxygen or water, it is often used to protect other metals, such as iron and steel, from corrosion. Tin is also added to other metals to make superconducting magnets. And tin is combined with fluoride in some toothpastes to help fight microbes and tooth sensitivity. Lithuania was the first republic to declare its independence from the Soviet Union in 1990. Following the Soviet occupation, Lithuanian workers made a shocking discovery while digging at a former military base: a mass grave with more than 2,000 bodies. There were few artifacts with the bodies, such as clothing or weapons, so local authorities had little evidence to help them identify the victims. But some tin buttons were finally found among the bones that changed everything. When the workers cleaned the buttons, they found traces of decorations in the tin. These decorations helped archaeologists identify the source of the buttons and the bodies. They belonged to one of the mightiest armies in European history, the army of the French military genius, Napoleon Bonaparte. In addition to helping identify the bodies, the tin buttons may actually hold the secret of Napoleon's greatest defeat. In June of 1812, Napoleon invaded Russia. He brought with him the largest army the world had ever seen, nearly 500,000 soldiers. The Russians couldn't hope to defeat Napoleon's army in battle, so instead they retreated. As they fell back, they devastated the land. They destroyed crops and buildings and left little food or valuables behind them that Napoleon and his troops could use. Napoleon was forced to chase the Russian army for months in a deadly game of cat and mouse. The French supply lines were stretched very thin, and the troops began to weaken. By September, the French army had lost 1/3 of its men to starvation, fatigue, desertion, or hit-and-run raids. Finally, the Russian army turned to fight, just 70 miles outside Moscow. More than 100,000 men died in the battle, but neither side claimed victory. Again, the Russians retreated, leaving Moscow empty. Then a fire swept through the city. Napoleon and his troops now had no food and no shelter. By mid-October, Napoleon gave in and ordered his troops to begin their 500-mile march back to France. But winter came early. Soon Napoleon's troops were faced with starvation and fatigue and freezing temperatures. The harsh winter claimed more French lives than the fighting had. Of Napoleon's army of nearly 500,000 soldiers, only 10,000 men survived to make it back to France. Although there was little direct evidence to support it, many believed that the tin buttons on the French uniforms were partly to blame for their casualties. A unique property of tin is that when its temperature drops below 56 degrees Fahrenheit, the shiny silver-white metal turns into gray tin. Although they are chemically the same, gray tin is non-metallic and powdery. It is possible that the frigid Russian winter turned the tin buttons on the French uniforms into crumbling gray tin, rendering them useless and leaving Napoleon's troops even more exposed to the cold. And his crumbling army may have been the victim of crumbling buttons of tin. Did you know? The process in which white tin turns crumbly and gray at low temperatures is called the tin pest, tin disease, or tin plague. This naturally occurring chemical process was first observed hundreds of years ago on tin organ pipes in unheated cathedrals in Europe. People of the day thought the transformation was the work of the devil or caused by a strange metal disease.
The ancient Romans are responsible for many inventions that we still use today, such as plumbing. Despite the fact that they relied heavily on pipes made of lead, a metal that is poisonous to humans after prolonged exposure, the Roman civilization was one of the most successful of all time.
What made ancient Rome so successful?
Rome in general was able to expand very well because they had such a powerful army and they were so well organized.
I think their structure of government made it really successful.
The civilization unified the people. They were able to overtake barbarians in outer lands and bring everyone in. Everyone was represented in the Senate, supposedly.
Definitely in each area, they grew and expanded and put a senator or a governor.
They were able to spread their culture to everyone so that everyone believed in what they believed in.
They had a system of trading. They had monetary, they had government. It was really amazing.
Element number 82 on the periodic table is lead. The atomic symbol for lead is Pb. Lead is a dense bluish-white metal that is very soft and pliable. It is corrosion resistant and a poor conductor of electricity. Lead gets its unusual atomic symbol, Pb, from the Latin word plumbum, which means plumbing, because lead was often used in ancient plumbing systems. Lead is classified as an other metal. It lies in the periodic table's 6th row, period 6. Each atom of lead consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of lead, its nucleus has 82 positively charged protons, plus 125 uncharged neutrons. Lead has 82 negatively charged electrons to balance its 82 protons. These electrons are found in 6 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, xenon. Xenon has 54 electrons distributed among 5 orbital shells. Lead has 28 more electrons than xenon. The first 2 electrons are found in the sphere-shaped 6s orbital shell. The next 14 electrons fill 7 lobe-shaped 4f orbitals. The next 10 electrons fill the clover-shaped 5d orbitals. And the final 2 electrons are distributed among 3 lobe-shaped 6p orbitals. Since the electrons in the 4f and 5d orbitals are at a lower energy than those in the 6s and 6p orbitals, only the 4 valence electrons in this 6-level shell influence how lead interacts with other elements. Pure lead has a beautiful silver appearance, but it tarnishes quickly when it is exposed to air. Lead's low melting point of just over 600 degrees Fahrenheit makes it an easy metal to work with. The lead here is heated and poured into a 2-chamber metal mold, where it soon cools and solidifies into the shape of the mold. Lead is poisonous and builds up in the human body over time, so it is no longer used to make toys, wall paints, pencils, or other products that might come into direct contact with people. Lead is most commonly used in the production of lead-acid batteries, such as those found in automobiles. Its high density makes it a good shield against X-ray and gamma-ray radiation, so it is often used in X-ray machines and nuclear reactors. Lead is toxic, and repeated exposure can lead to poisoning, which can be fatal. The use of lead has been traced to the ancient Egyptians around 4000 BC. The Egyptians used black eye makeup made of ground lead ore mixed with oils. Other ancient peoples used lead to make corrosion-resistant glazes for ceramics, works of art, ornaments, and even weights for fishing nets. But lead may have been partly responsible for the downfall of one of the greatest civilizations of the ancient world, the Roman Empire. The Romans created a highly advanced civilization. They were particularly good at redesigning and improving inventions of other civilizations. One such invention was the aqueduct, a system that brought clean water from distant mountains to cities and towns. Parts of these aqueducts were rows of arches that used gravity to transport water through lead troughs running along the top arch. The stone arches were especially useful for carrying water across low plains, valleys, and riverbeds. But most of the aqueduct system was a series of underground pipes made of clay, bronze, or lead. These pipes and conduits sometimes stretched as long as 40 miles. Once the water reached Roman cities, it was distributed through lead pipes to public fountains, government buildings, and private residences. Many Roman drinking vessels and cookware were also made of lead or coated with lead glazes. The Romans even used lead powder to preserve food and improve the taste of wine. Some historians believe that the Romans' widespread use of lead may have poisoned them slowly and may have contributed to the downfall of their empire. Modern-day scientists have discovered that even small amounts of lead can be dangerous to consume. The human body cannot distinguish lead from calcium, which is an important element for healthy bones and other body functions. As a result, the body does not get rid of lead once it gets into your system. Over time, this lead buildup can be extremely harmful. Lead poisoning can bring about stomach pain, nervous system disorders, and it can cause damage to the kidneys, red blood cells, and brain. Eating lead is especially dangerous for young children because it can affect their developing brains and cause learning, visual, and motor problems. Over many years, the Romans' ingestion of lead could have built up to dangerous levels, leading to physical and mental problems, and contributing to the eventual collapse of their once great empire. We may never know everything that led to the empire's fall, but it seems clear that the Roman love of lead may have played a part. You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
What properties do the other metals share?
Why did the Romans use lead in their plumbing?
If you'd like to learn more about what you've just seen, go online or check out these books at your local library.
As you watch the second half of this program, keep these questions in mind.
What makes aluminum such a useful metal for cars?
What other elements might be used in the cars of the future?
Ever since the introduction of the internal combustion engine in the 1880s, the use of automobiles has increased in the United States. And car designers today are racing to use elements in new ways to make the cars of the future cleaner and more efficient.
What do you think the cars of the future will be like?
Hopefully, I would like to see the cars of the future be more fuel efficient.
I think that the cars of the future will be safer for the environment since there are so many problems with the atmosphere.
I think it might change to like electric cars instead of gas because the gas prices are going up.
Maybe they wouldn't have wheels like hovercrafts and they'd float on the ground.
I don't know. I don't think the cars will change much. Probably stay the same. They might be able to fly eventually.
Well, I don't think they will fly because that's just a little crazy.
There are cars that don't use gasoline and don't pollute. All that's keeping this car going is sunlight. This Honda would be the car of the perfect tomorrow, if only it didn't cost millions or stop when the sun goes down. But cars that run on little more than thin air needn't be a dream. They could be reality sooner than you think. Stirred into action by former President Bill Clinton, U.S. industry began reinventing the American car for the new century. By 2020, the thirstiest cars on the planet will have gone for good.
I think the key trends will be both in the way in which we design and develop cars, and the products themselves will almost certainly get lighter in weight, more technologically complex. In order to meet those challenges, we'll see a lot of changes in materials into much less conventional materials than we've used up to now. Substantial changes in powertrains, a lot more electronics on board, and so on. Basically, much more technologically intense, but hopefully at the same kind of cost as today's vehicles.
In windowless, high-security laboratories, prototypes of the new generation of 90-mile-per-gallon cars are already under development. In a corner of Detroit, Chrysler's executives take an early look at the cars of tomorrow. They must decide in which new technologies to invest. It's not an easy choice. Tomorrow's cars may look familiar, but under the skin, they'll be unlike anything on the road today. Elements and technologies that have seldom, if ever, been used in car manufacturing will increasingly be used in the cars of the future. Dressed in plastic and the strong, lightweight element aluminum, these models tip the scales at a fraction of the weight of current American cars. Few of them have a traditional engine. Some don't have an engine at all. But these aren't dream cars. These are cars we could all be driving in 20 years' time. The more fuel we burn, the more we pollute. Most people notice the fuel gauge only when there's an oil crisis or when the price of gas skyrockets. Many want to change that. This is Ford's vision of the American car of the future. No smaller and no slower than today's 3-liter gas guzzlers, the P2000 has just a tiny 1.3-liter engine. Further down the pipeline, P2000 has another engine, one with no moving parts, originally developed to work in space. But neither can do their job if the American car doesn't lose some weight first.
To get the fuel efficiency out of either of these powertrains, we need the vehicle to be very light. And we're looking at extensive use of aluminum on the body, as well as magnesium in other components, and certainly some composites. Because if we don't get the weight down, we really can't get the extremely high fuel economy we want.
The iron and steel used in today's cars is heavy, and the heavier a car is, the less efficient it can be. But in a sports car like this Volkswagen prototype, using lighter elements means the same engine can push the car more quickly down the road. In a family car, the less it weighs, the farther it will go on the same amount of fuel. When money is no object, a 200-mile-per-hour sports car isn't made of steel, but exotic synthetic fibers and rare elemental metals like titanium and magnesium, materials that can cut the weight of a car in half and double its price. The first 21st century family cars won't be made of rare metals or synthetic fibers because that's too expensive. But how about recyclable aluminum? We throw away billions of aluminum cans each year, more than enough to make the 20,000 or so sports cars and limousines already made from the metal. In the future, lightweight cars won't be the preserve of the rich. We could all be drinking out of recycled cars or driving recycled cans. The aluminum-rich Plymouth Prowler is all about the future.
A typical steel body structure and body panels will weigh about 900 pounds. The potential in aluminum exists that that body can weigh as low as 300 pounds, which is approximately 65% weight savings compared to a steel structure. For us, this is very, very important because we can improve the mileage of a vehicle depending on how much weight we save. For every 100 pounds that we save, we improve the mileage by 1 mile per gallon. In addition, we can reduce our emissions because now you have less power to achieve the same acceleration and the same performance of a vehicle.
One day, Plymouth could make all its cars from aluminum, but there are problems to iron out, literally. Unlike steel, the element aluminum is rigid and doesn't bend easily into hoods and fenders. So achieving the quality of fit and finish we expect remains a problem. And although costs are dropping, aluminum is still 3 times more expensive to produce than steel.
Although the car is very, very exciting, we would like to do the same thing and achieve the same performance, but for a much higher volume car. Currently, a body structure in aluminum costs about 2.5 times the cost of steel. We think this is one of the last hurdles that we have to overcome before you can really see a $10,000 all aluminum vehicle.
This is the P2000, the aluminum car of the future. Designed to use just 1 gallon of fuel for every 90 miles, it's made almost entirely from aluminum. But this is only a simulation. Before work starts on the real car, engineers are applying this technology of tomorrow to the cars of today. A typical American car weighs 2,800 pounds. On average, 2,000 pounds of that is steel and iron. Ford plans to cut that by 75% by using aluminum throughout the entire car. This P2000 prototype weighs less than 1 ton, a 40% reduction, thanks to aluminum. On the road, it hits 60 miles per gallon. But as long as aluminum remains expensive and difficult to work with, engineers will continue to look for solutions to keep costs down and save weight. They're finding them in the strangest places. In addition to soda bottles, Cascade Engineering in Grand Rapids, Michigan, makes giant industrial and domestic dumpsters. It's an odd place to discover a technology that could revolutionize the way cars are made in the developed world and put thousands in the undeveloped world behind the wheel. Smog. This is the reason America needs to see the end of gas guzzlers. It's been 20 years since California first decided to do something about its smog. 2 decades of legislation haven't made cars in California any more efficient, but it has cleaned up what comes out of tailpipes. Our engines produce a number of gases. Oxygen and water are harmless, but many are not. Nitric oxide from auto exhaust combines with oxygen in the air to form brown nitrogen dioxide, smog. Another engine emission, carbon monoxide, is poisonous. And when nitric oxide and the hydrocarbons our engines release are exposed to sunlight, a photochemical reaction takes place that forms ozone and other harmful compounds.
In the 1960s, before we had any regulations, it took about 210 grams of fuel to get a passenger car 1 mile. Out of that car came about 10 grams of unburned hydrocarbons per mile directly into the atmosphere. Since the 60s, of course, we've had redesign of our engines. We've taken weight out of the vehicle. We've totally put electronic control systems into our automobiles. And today, a typical family-sized car requires only 110 grams of fuel to get 1 mile, just about half of what it used to. Now, out of the engine comes about 2.5 to 3 grams of unburned hydrocarbons. But a big change has been the advent of the automotive catalytic converters. Gases come in. The catalytic converter converts them to harmless emissions out the other side. In the case of hydrocarbons, we've gone now from 2.5 to 3 grams per mile to about 0.4 of a gram per mile. Basically 96% reduction from where we were pre-emission regulations.
Hybrids have the best of both worlds by employing a pollution-free electric motor and a flexible and longer-range internal combustion engine. In a so-called parallel hybrid, there's an engine at either end of the car. At low speeds, in polluted city areas, an electric motor drives the front wheels. An electronics black box, which controls the electric motor, switches over to the gas engine as speeds increase. Hybrids have a smaller battery pack, since they can be charged on the move by the gasoline engine. Here is a high-efficiency diesel engine, but it could be any fossil fuel burning, so-called heat engine. The presence of a gas engine in the drivetrain means hybrids are less green than pure electric cars, but they are more practical. But there's not a car maker on the planet not currently busy mating a gas engine to an electric motor to develop what some observers are already calling hypercars. This Renault has tiny electric motors inside its rear wheels, and under the hood is a Mitsubishi-style direct injection gas engine. In town, up to speeds of 25 miles per hour, it's driven by the motors. Above that, the black box switches to the gas engine, which simultaneously recharges the batteries. Renault says its new generation family car is up to twice as efficient as a regular car, and it would be even more so if it didn't have to lug 300 pounds of batteries around with it. In the second half of the century, when we can no longer take fossil fuels for granted, lies the hydrogen age. Car makers in Germany are already running small fleets of traditional cars, adapted to run on the pollution-free element hydrogen. Clean, but not efficient, these cars are a prelude to what could be a most dramatic development. This Toyota has an electric motor that is powered by a fuel cell. Originally developed for the Gemini space program in the 1960s, fuel cells are likely to change the way we use our cars and the way we live our lives. A fuel cell combines hydrogen, the green atoms, and oxygen, the blue, to produce electricity. The only byproduct is water, so pure you could drink it straight out of the exhaust pipe. In a fuel cell, a platinum catalyst splits atoms of hydrogen into protons and electrons. The tiny protons on the left escape to bond with the oxygen on the right to make water. Trapped by a membrane, the larger electrons flow into an electric motor. In fuel cell cars, like those under development at Toyota and Mercedes-Benz, the fuel cell replaces the gas engine and the batteries. There's still an electric motor and a powerful electronics box. Fuel cells are normally grouped together in stacks. They get their hydrogen from a reformer, which extracts it from other liquid gases like methanol. Storing hydrogen on board still presents a problem, and there's currently nowhere to fill up with hydrogen. Mercedes-Benz is leading the race to introduce fuel cell cars. Mercedes partner Ballard has already developed fuel cell-powered buses, but at Mercedes, the work concentrates on miniaturizing the technology to fit cars. Spectacular progress has been made in increasing the amount of power a cell will generate relative to its size. Cells that were once too big for anything but buses or vans will now fit cars. This A-Class Mercedes-Benz, one of the smallest cars in Europe, has been converted to take a fuel cell stack. The bulky equipment in the rear is not the fuel cell, but the reformer and the methanol tank. Separating hydrogen from water or other sources is still an expensive process. And onboard hydrogen generation like this is the only way forward until gas stations can economically start pumping hydrogen. There are 300 fuel cells on board this prototype A-Class. That's enough to power the vehicle to beyond 80 miles per hour and give it quick acceleration. The key to releasing the remarkable potential of fuel cells is finding a way to supply them with hydrogen. A technique exists that could replace refueling as we know it. Instead of visits to gas stations, we could one day plug in solid blocks of fuel, enough to drive thousands of miles without stopping to fill up. This astounding technology wasn't discovered in an engineering shop, but by a husband and wife team researching one form of the element carbon.
Graphite nanofibers are this material. They have the property to act very much like a sponge, in which they can soak up hydrogen to produce a very high density system contained in a very small volume.
Materials do exist that will store hydrogen up to typically 4 weight percent, but for the average driver, that would not give you a very long driving range. We needed a material that could store significantly larger amounts of hydrogen so that we could go for extended trips in a car without having to worry about refueling. So this material allowed us the opportunity to put significantly larger amounts of hydrogen into a material than had hitherto ever been achieved. We grow this material from small metal particles interacting with hydrocarbons. And the key feature which turned out is the ability to manipulate the behavior of the metal particles in such a way that they create honeycomb structures which are ideally suited for the storage of hydrogen.
This is a 1 liter container. If we put hydrogen at high pressure, we'll be able to drive approximately 1 mile. If on the other hand, we fill the canister with graphite nanofibers, we can now store sufficient hydrogen to be able to drive 25 miles with exactly the same volume canister. If we fill our current gasoline tank of 50 liters with graphite nanofibers, we should be able to have sufficient fuel to run 1,250 miles on a single charge.
Graphite nanofibers could be the key, not to the next generation of cars, but to the generation after that. The first cars of the hydrogen age. The key to building these hydrogen-powered featherweight supercars of the future will come from an alliance of research, industry, and dreamers.
You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
What makes aluminum such a useful metal for cars?
What other elements might be used in the cars of the future?
We hope you've enjoyed this assignment discovery analysis of the other metals. If you'd like to learn more about what you've just seen, go online or check out these books at your local library.